Hello, this is Ray Anke from James Madison University, and this is the DNA Subway Purple Line video tutorial number 3. In the last video, we set up this data 2 analysis, which is doing a couple of important things. It's trimming and filtering low quality reads, and it's also assigning taxonomy to all of the sequencing reads in each of the samples to equate each sequence read to a taxonomical unit. So now that data 2 is finished running, we now have this green V, so we can go in and view the data outputs. And there's 3 different results we can look at: the trim table, stats, and representative sequences. Let's start with stats, because this is going to give us our QC filtering results. So this is going to tell us about the quality of our data. So we already saw those quality plots and the demultiplex outputs, and we saw that for the most part our sequence quality was pretty good. We had some low quality reads on the end, and then we set up our trim job. What we have here is all of our samples, our 20 samples, our input reads per sample, filtered reads per sample, and the percentage of input reads that pass the filter. So this metric right here is very important. So you can toggle this to get your least and most descending order in terms of lowest and highest. I always like to look at my lowest. I want to see what my worst sample looks like. So in this case, my worst sample, almost 80% of the reads passed filter, which is really good. So if you have a case where this number is very low, say like below 50%, that could be an issue. That indicates that perhaps your sequencing quality is not great for high quality analysis. And then you have some other metrics down here, which are doing some other just giving you other quality metrics that we're not going to talk about here. Okay, so that's the stats table. It's important to look at the quality of your reads. Next is representative sequences. So this is the other feature of data 2, one of the other features where it's taking your sequences and it's assigning taxonomy to each sequence. So you have some table data here. This sequence count here is an important metric. This is telling us that of all of the thousands of sequences that we have, there were 361 unique taxonomical units. And then we have some metrics for length. The sequence table down here lists out each of those. What do we have? 361. There's 361 unique sequences. This is telling you what each of their sort of alphanumeric feature IDs are, the length of the feature. And then here's the actual sequence of the feature. And you can see these are hyperlinks. If you were to click on any one of these, it sends it to NCBI BLAST. And if you wanted to, you could set up a BLAST job to see what that individual unit is. We're not going to do that now, but if you wanted to, you could do it right there. Okay, and the third result is the trim table, and we actually need some important information here. So let's go into the trim table. So for our next step in the purple line, we need to know the maximum and the minimum number of features per sample. And so here in this first tab, in the overview tab, which is the only tab, I'm going to skip the other tabs for now just because we just need a little bit of simple information here. We have this frequency per sample. And again, we have, instead of talking about sequencing reads, we're now talking about features. So the sample with the lowest amount of features was 623, and the sample that had the maximum amount of features had almost 6,500 features. So I'm going to jot these two numbers down. So my minimum frequency is 623. My maximum frequency is 6585. So you need those two numbers for future steps in your analysis. And then I will go over here to the interactive sample detail. I'm going to skip talking about all this stuff up top. What I am going to show you though is this table that is now listing each of our 20 samples, and it's showing us the amount of features per sample in descending order. So this will become important too, because we have our lowest samples. We'll have to make a decision about what we want our sampling depth to be for our last few steps of the analysis. And we'll have to decide if we want our sampling depth to be, let's say we want our sampling depth to be 1,000. Well, that means any samples that have less than 1,000 features will be cut out of the analysis entirely. So those samples will completely drop out. So that may influence how you want to do your downstream analysis. You may say, well, I'd like to keep as many samples in as possible. So maybe I'll set my sampling depth for 830 and just drop out fewer samples. The next step we're going to run, the alpha rarefaction step, which is now open, it's in this clustering sequences run. This will give us some insight after we run it as to what sampling depth will be most beneficial for our analysis. So now that this step is open, let's go ahead and set up our alpha rarefaction step. And I've already set this up, so I'm going to go ahead and set up a new job. And what we have here is we need to input the minimum and maximum depth of our analysis. So how many features do we want purple line to incorporate into our analysis? And the defaults here are 1 and 3000. We'll keep the minimum depth set to 1, the default 1. But for this max, this is the number that we want to plug in from our specific data. So remember, our max frequency was 6585. So that means that each of the, our top sample had this many features in it. So we're going to go ahead and set those as our parameters. And I actually already submitted that. You would hit submit. I actually already did that. This takes not that long to run. Once it's finished running, you can then view. So we'll go ahead and view the data output. And what we'll get is this alpha rarefaction plot. So this is another one of these interactive plots. It has some things you can choose here. We want to look, we want to use the sample metadata column of description. That's going to list all of our samples here. So this is all 20 of our samples. In terms of what we're looking at are diversity units on the y-axis here, and there's a few different ways we can look at it: a faith PD plot, a Shannon diversity plot, or observed OTUs. I find Shannon diversity or maybe observed OTUs to be the most straightforward to look at. So what we're looking at is observed taxonomy. Let's look at Shannon diversity. We're looking at Shannon diversity. So this is the amount of diversity in our being detected in our samples, and on the x-axis we have our sequencing depth. So starting at 0 reads, we obviously have no diversity, and as we incorporate more and more reads into our analysis, the software is determining that we have a steep increase in taxonomical diversity up to a point, and then you can see that it plateaus off. And so what that is indicating is that it's not necessarily adding more and more and more and more reads or features to your analysis doesn't necessarily increase the richness of your diversity. And so what this allows you to do, this plot allows you to kind of make a decision about how many features are going to be enough for your analysis, so we can decide what's the cutoff. Because remember, you can see that these samples down here that had less than 1,000, if we set it, like we talked about, if we set the sequencing depth to 1,000, all of these samples are going to cut out. So this is where you have to make decisions. Do you want to, how much depth do you want to have? What this plot is telling us is if we have, it looks like we're plateauing off here at about, that looks to be, I'm going to say 700. So if we set 700 for our sampling depth, that means we're only really cutting out 1 or 2 samples. Or you can say our lowest sample feature was 623. That's this one right here. We could just run it at that sampling depth, and that way none of our samples will drop out. So this is where you have to make a decision. It's actually probably a good idea to run Purple Line a few different ways. So maybe one way to run it would be to set your sampling depth for 1,000. And then another way to run it would be to set your sampling depth for your minimum frequency, which in this case would be 623, and see how they differ. You want to use this as an opportunity to get the best data possible. So you know that you want to set it up in multiple ways. And using that analysis, you're going to go over here to core metrics, which we'll talk about more in the next video. you're going to punch in your sampling depth here. So this is where you define, do you want to use that 623 number? That means all of our samples will be retained, none will get cut out, but we won't necessarily have the most diversity. So this is going to say purple line is going to only factor in 623 features for all 23 samples, for all 20 samples, even though many of the samples have many more than that. We can set this to a higher number, say like 1,000. So purple line will factor in 1,000 features per sample, but that's going to cut out all of your samples that have less. So this is where you may want to branch off and do several different types of analyses. Maybe you have enough feature depth, enough features in your samples that this isn't an issue. The other thing you're selecting here is the classifier. So we have the different primer sets, cytochrome oxidase, fish 12S, Silva 16S, green genes. This is another 16S. So even though there's two 16S primers, we're recommending that you use the green genes 16S primers. And then you will submit this job. I'm actually going to run it at the minimum so I can retain all my samples. And then you'll submit this. And then once this finishes up, the core metrics, we're essentially telling Purple Line, please consider 623 features for all 20 of my samples. That's running now. Once that's finished running, that's going to open up these three stops: alpha diversity, beta diversity, taxonomical diversity. And again, we'll get to take a look at those outputs based on only factoring in 623 features. You can certainly, and I would recommend running this again using more features and taking a look at these same outputs. So we'll take a look at these outputs in the next video.